Well, hey, Ted, how's it going?
Not bad, not bad.
How's the weather out there in Seattle?
Uh, well, it's actually been kind of nice the last 3 or 4 days, or maybe a week. Temperate, not cold, not hot, not wet.
We're still jumping over ice dams here in Boulder. So, a whole bunch of people are really excited to find out what the differences are between the MK1 and the MK2. Personally, it didn't take me very long to hook up the MK2 and give it a listen and to pull myself off the floor, pop my jaw back up like, oh man. I mean, the difference is huge sonically, but maybe you can go into some detail to help those watching understand, in as simple as you can, the difference between the MK1 and the MK2.
Well, let's talk about the easy ones first.
Good.
Everything that was in the Mark One is in the Mark Two, but better. So we're using better quality digital switches. We're using better quality filters for the clock, better all the way around, a much better power supply designed from scratch. Um, but the next step is to add digital isolation to all of the inputs and outputs because we're just trying to get rid of noise. Noise is the big evil, right? A black background is what you want. Noise destroys that. So every place I could find to get rid of noise, I did. And one thing is galvanic isolation all the way around, cleaner power supplies, cleaner regulators all the way down through to the very bottom. I'm using the best regulators available. They're not cheap, but they pay, they pay for themselves. Um, and then inside the FPGA, I rewrote all of the upsampling filters. I rewrote the sigma delta modulator, all to have more accurate data, bigger dynamic range. I mean, I don't remember the exact numbers, but on the order of 64 bits for some of the integers and stuff like that. And
Wow.
a
And we're
double,
and we're only starting with 24 bits or maybe 32 bits.
right, but the longer your filters get, the more accurate your coefficients have to be because you're adding a huge number of numbers together. And if you don't have extra bits to hold any overflow, you've got a problem. And the the longer your filter is, the more accuracy you need in each of the ones so that when you add them all together, they'll get to one. So that's one source of it. In the sigma delta modulator, uh, you just get um, more detail if you add more bits. It's just about that simple. Now I changed the filtering I'm using in the sigma delta modulator, and I changed the order of it and stuff like that to try to get cleaner outputs on that as well. Um, the galvanic isolation was more expensive than we would like, but it and it affected everything on the digital card, right? Because every digital input is isolated.
Well, we hear a lot about this galvanic isolation business. Tell us in Ted's own words, what does that mean? And once we understand what it is galvanic isolation is, why do we care?
Um, Almost any circuit that you have is going to have a certain amount of noise on it. But there's also ground loops and things like that in our system. And a ground loop is a radio receiver, and it's the extra current induced in it is proportional to the area of the ground loop. And of course, how much flux is coming in from wherever.
Mm-hmm.
So if you put like a magnet in the middle of, you're not going to get anything. But if you keep moving it, you're going to induce a field everywhere. And the same thing with RF and everything else. So to break ground loops, you need to have some kind of galvanic isolation. That means, that if these two are connected together, you can't get a DC voltage between them.
Okay.
So in a sense, a capacitor could break ground loops, but that's a filter, and we don't want filters on our analog outputs. We don't want so on and so forth. And for digital, we have so many different digital rates that you stick in a capacitor and you're going to roll off the edges, which adds jitter and so on and so forth. So you want a custom built device for isolating digital data. Now, one of the strange things is there are a boatload of digital isolators out there. I mean, people have heard of optocouplers, right? The problem with those is they're slow.
So
right?
just so everybody knows what we're talking about, what we're trying to do is break the physical electrical connection between, say, your computer and your DAC.
Right.
And when we break it, now there's no way for the signal to get in. So now we have to come up with another way to couple it. And in this case, you're talking about using light beams, lasers to go.
And that's a pretty standard way of doing it.
Yeah.
And for a long time, optocouplers were just way too slow. Now you can pay more and get optocouplers that are fast enough. There are other technologies. Some people use capacitors in a little chip. They have one set of problems. I'll get to that in a moment.
Okay.
Some people use transformers in a little chip. The problem with both transformers and capacitors is you can't pass DC, right? So you can't say, I'm up or I'm down. So instead, these little isolators build a 1 gigahertz radio frequency or something like that. And when the data is high, it's sending it. And when the data is low, it's not. So it's called on-off keying. Well, putting a little radio transmitter inside your DAC is just not a good idea. So any of the digital isolators that are out there were built for audio. They were built for industrial applications where you have to isolate one side from the other, and they might have differences of like 200 or 400 volts, right? So it's really important to isolate it that way, but you're in a noisy environment in industrial setups. So the fact that the chip itself generates, relatively speaking, a very small amount of noise doesn't bother anybody. As long as it doesn't cause the bits to change, they're fine. So a lot of devices out there that have digital isolation have bad digital isolation. So I spent some time trying to find the best digital isolation I could. And it's based on a pretty obscure quantum mechanical connection. Sounds like I'm blowing smoke, but it's magnetorestrictive coupling. And the beauty of it is you don't have to have, let's see if I can say this right, you don't have to have current on your receiving thing, right? You can just have like an RS 232 isolator, would just have to take the end of the wire, go in one side and the other, and you don't need a power supply there. So it can be a much quieter isolator than capacitors or transformers, because it's just paying attention to the magnetic field induced by a current through a wire. It's either one way or the other. And these, when I first started doing it, were pretty reasonable isolators. They only cost twice as much as any other ones on the market. Now they cost 4 times as much as any other one on the market, but it's still worth it, because you can hear with your ears what having these isolations all over the board does. And then the next thing that made the Mark II a little more complicated than we would like is if we want to isolate, say, the I2S inputs, we have to have active components there to receive the signal. And that means we have to have power.
Mm-hmm.
And if you're trying to have this isolated from the rest of the board and have power, you have to do something. You have to build an isolated power supply. Once again, you can go out and buy all sorts of isolated power supplies, but many of them are little switching supplies. They
Mm-hmm.
have all the problems that people, all the bad problems people associate with switching supplies, generating all sorts of noise at frequencies that aren't related to the clocks in the rest of your system and all that. So I built a discrete supply that's running at a frequency that we choose so that it doesn't interfere with the audio. And all it's doing is pulling one wire this way or this way through a capacitor. So on the other side of the capacitor, you see the voltage is changing like this. And then I filter the bejesus out of it on both sides. But
And you get your DC.
yeah, and there's some pretty cute tricks you can play to not just have diode losses on the other side. This is low enough current that I can actually use cross-coupled MOSFETs.
Okay.
And that allows me, instead of having two diode losses on a full wave bridge, which is, 1.4 volts, and I want a 5-volt supply. 1.4 volts out of 5 volts is very significant.
Yes.
It's a power loss, it's inefficiency, and it gets too low of a voltage. The classic solution is to just jack up the voltage you're sending across.
Right.
But using MOSFETs, you can do a better job because they can have very close to zero resistance.
Mm-hmm.
And so that works if you run it fast enough and you design it right. And fortunately, we can do that. On the analog side, for the outputs, it's pretty easy. I've always liked transformers in my DACs, and one of the reasons is it gives you galvanic isolation.
Sure.
And that's important. The other thing we did, though, is every place in the system that we have galvanic isolation, you can turn it on or off.
Mm-hmm.
Because some cables work better if the source is grounded. Some cables work better if the destination is grounded.
Mm-hmm.
Some work better with both ends grounded.
Mm-hmm.
So on a given system, it might sound better with galvanic isolation
Galvanic. Yeah.
Than on, just because of other things in your system.
Mm-hmm.
So we built this to be compatible with the DS by default. In other words, nothing's isolated, but you can go in the menus and pick what you want to isolate one by one.
So just to be clear, if you just got a brand new MK2, do they come isolated or do they come not isolated?
They come not isolated so that if you had a Mark II in your system, you'd have the same noise that you had in the Mark II. If you isolate something that shouldn't be isolated, you might end up with hum and things
So
like that.
if I'm a new MK2 owner, I'm going to want to be careful and go in and try and see.
Yeah, and there's nothing better that we can tell you than try each input and each output one by one so that you can adjust it to be the best for your system.
Now, in my case, I went and isolated all the inputs. Well, all the inputs. I mean, I don't use that many inputs. I use USB and I2S. And I found that isolating it was noticeably better.
Yeah. I've taken a prototype of this to a lot of different systems, and it's all over the map whether isolation is better or not. I mean, if somebody has a really clean system with no ground loops in it, isolation isn't going to make nearly the difference that it would make, say, in my system where I've got digital things all over the place, USB cables all over the place, telephones, you name it. All of those things are evil.
Yes.
Because they can cause current in a ground loop. That current is noise, and you have to make sure that everything in your system is doing its best to cancel out that noise. One thing that helps is, say, balanced cables, right?
Yeah.
Some systems you use a non-balanced cable, and you end up with hum. You put the balanced cable in, the hum's gone. That's certainly not true with all systems. We know people that have unbalanced cables are happy as clams. And that's true with galvanic isolation. It may make a huge difference for you, it may make no difference for you.
Mm-hmm.
But it's worth experimenting with on each individual system.
That's good to know.
Another thing that we changed was I really wanted to try to make the Mark II a better citizen, if you will.
Mm-hmm.
So one of the things we did is we had the outputs more configurable than the DS.
Okay.
So
what does that mean?
Well, the most obvious thing is you could choose to not galvanically isolate the output.
Mm-hmm.
But another thing you can choose to do is run the RCA balanced. Just put it all the way across the transformer. You'll get twice as much voltage. And if we galvanically isolate, then it doesn't matter that we're using the ground for one half of the transformer, right?
Mm-hmm.
And so on the other end of the system, if your system can handle a really hot, unbalanced setup, you can get a louder voltage.
By 6 dB.
Yep. And that's not insignificant.
No, that's double the voltage.
And although it's a digression for what I was talking about, we're now using the standard output levels for the Mark II of 4 volts RMS full scale
mm-hmm.
balanced and 2 volts RMS full scale unbalanced, which is pretty standard for CD players and stuff in the industry. And the DS Mark I was 3 dB down from that, about a factor of 1.4.
Right.
And so once again, we're being better citizens by working with more systems because we're using more standard levels. And that extra, anytime you have a louder signal, it sounds better to people, right? I mean, that's just true. So you put it in your system and it'll be more comfortable, if you will, being slightly louder. There's some other weirder things we do for the configuration of the outputs. We let you float the shield on your XLR connector.
Mm-hmm.
I mean, so XLRs have, positive signal, negative signal, a ground, and then the shield. Mm-hmm. And the ground and the shield may or may not be connected on your source or destination or in your cable or not. And some people really need the shield grounded at the source and the ground line hooked up or not hooked up.
Right.
And that's another option we have, is we can just not hook up the ground line in your balanced connection.
Yes.
Because if the receiver is truly balanced, it's only going to operate on the difference between the signals.
Mm-hmm. Mm-hmm.
And then you don't care if the ground levels of the source and destination differ. It just doesn't matter. So that can get you a cleaner signal. A lot of systems aren't prepared to do that. If you have op amps in your receiver, you can't get too far from
right.
the grounds. So if the grounds stay within 2 or 3 volts, may or may not work, right? But if you hook up the ground wire between them, it will work.
Right. And so you have all these options.
Right. And so you can disconnect that ground wire. And if it sounds better, go for it. If it doesn't, put it back.
Exactly.
And once again, that's something we wanted to be like the DS by default. The law of least surprise, right?
Ted's law of least surprise. I love it.
It's not my law, but it's important for like user interface design, right?
Right.
When somebody does something, it's really bad if it's very surprising what had happened. You want everything in your user interface to be what you expect,
mm-hmm.
not a surprise. And we want the DAC to fit in your system without being a big surprise, at least in the negative sense.
Yep.
We'd love it to be a big surprise in the positive sense. Along the lines of lowering noise, I briefly mentioned, but I spent a lot of time designing the power supply to be a better citizen. And what I mean by that is many of the power supplies in audio systems are half wave or a full wave rectifier.
Mm-hmm.
And what that does is, as the AC voltage comes up, at some point it gets higher than what your system has in it,
Mm-hmm.
and then it starts conducting.
Mm-hmm.
And then when the capacitors in your system fill up to a certain degree, it stops conducting. What that means is everybody in your system is fighting for the electricity right at the peaks of the AC waveform.
Yep.
So I went out of my way to draw current evenly over the AC waveform. So you start drawing current much earlier. You don't draw as much near the peak, and then you keep drawing it a little bit later on the other side.
So that's typically known as power factor correction, right?
Yes, a lot of people use it as power factor correction, and the circuit I'm using is a circuit that was used for power factor correction for like CFL bulbs and stuff like that. They needed power factor correction horribly, otherwise they just hum audibly as well
Sure.
as visually.
Right.
So this is power factor corrected. I haven't measured the production units to know what it's at, but the simulations say it should be about 0.94.
And for people who don't know what we're talking about, a pure power factor of 1 means the voltage and the current track each other precisely, where a lower power factor, like say 0.7 or something, the voltage is rising and the current isn't doing anything. And then when it gets up to the peak, it jumps up like that. And as Ted was describing, a power factor of say 0.7, 0.65, which is common in a piece of electronics, means that as the voltage is rising, the current just stays just 0. And all of a sudden, near the peak of the sine wave, it goes way high. And this can cause all kinds of problems. And the ideal is 1. If you can have voltage and current tracking, that is ideal. So the Mark II DAC has pretty close to 1, at least in the simulations, but we got a lot closer, which is great.
Yeah, well, I have looked at the waveforms on the scope and they match the simulations, but I haven't literally measured
Sure.
the power factor. I measured the power factor on the TSS, which I derived the Mark II power supplies from, and on it I was getting 0.97.
Oh, that's excellent. That's excellent.
Yeah.
Where the MK1 was probably a 0.7 or so.
Yeah. It was definitely lower. And
yep.
the power factor
and that makes for noise
how
too.
horrible it is when you draw all your current in a few milliseconds, because that's where you need the biggest conducting wires all the way back to the power plant. In an argument's sake, is because you need your 80 amps now or whatever your system.
And that's one of the reasons that the power plant AC regenerators that regulate and will continue to put out as much current as asked for help, especially when you have a lower power factor. So this is all really good stuff.
And so I'm really trying to make the whole unit any way I can be nicer in people's systems. And, it sounds better. I mean, it's obvious that it sounds better. And that part of that is definitely because I'm trying very carefully to have cleaner power, cleaner outputs, ignore more crap on the inputs.
Yep. So, Ted, one of the things people love about the MK1 is the ability to get a new DAC every time that we do a firmware upgrade. And we used to call those mountaintops, and we still will. Will we be able to do that on the MK2?
Absolutely. I have to make it a little qualified though. A lot of the tricks I use to make the Mark I better won't work in the Mark II because I fixed those in hardware.
Okay, so just a bigger challenge.
Yes, it's a bigger challenge, but one of the things we're doing is we're using a more powerful FPGA in this system. It can do, about 2.5 times as much work per size, and we're using a bigger size.
Nice.
So the Mark I, the FPGA was almost always near full. Whenever I wanted to add a new feature, I'd have to go figure out how to do something else in there more efficiently to make room for it.
Mm-hmm.
And because I was near the edge of the thing, the tools were always taking half an hour, 4 hours to try to figure out how to fit it in.
Right.
And now I'm using about half of an FPGA to do better work. And that means that my compiles take 1 or 2 minutes. Well, that's wonderful in a lot of ways. It means I can try a lot more stuff per unit time. It means I don't forget what I was doing when a compile finishes and don't test it right and so on and so forth. But in addition to that, we put in 2 FPGAs.
Mm-hmm.
Now, that wasn't our original decision. That was forced on us by all the supply chain weirdness. We actually couldn't get the FPGA we wanted, so we got 2 smaller ones that were available.
Mm-hmm.
Now, the benefits of that is I'm not even using the second FPGA at all right now. In the future, one way we'll be able to grow is, just for argument's sake, putting the left channel in one and the right channel in the other.
Mm-hmm.
So they can operate in parallel and have the whole chip for each channel. Or we could do the upsampling in one and the sigma delta modulator in the other.
Mm-hmm.
And to make these work well together, I use 10 lines, each of which has about 8 times the bandwidth we need for any communication that's in the thing right now.
Wow.
So we have all the ability to send data back and forth we want. We can make round trips, 10 times without writing fancy code.
Well, so this is pretty exciting. So, I mean, the opportunities, while different than the MK1, could be really, really huge.
Well, and I've taken advantage of part of the extra FPGA space already. The Mark II filters are all at least twice as big as the Mark I filters.
Mm-hmm.
I don't know where the sweet spot is. You talk to Cord, they say you want 1 million taps. I don't think you need 1 million taps to get all the benefit. But the very short number of taps in a lot of DAC chips, 100 or whatever, is too small. There's no question about that. So, right now, I don't remember the exact numbers. I'm using 20,000 or something like that.
Mm-hmm.
I have room to grow now. And this might be of interest to people. It's a little technical, but it's not the number of multiplies I can do in an FPGA that's the limit. If you put in twice as many taps, you got to do twice as many multiplies per unit time.
Mm-hmm.
But you also have to have more than twice as much RAM to hold all of those coefficients.
Well, you do all the math.
Right. And so I mentioned that as the filter gets bigger, you need wider coefficients and you need more coefficients. So the amount of RAM you need for upsamplers grows faster than the length of your filter. And so I'm using up a lot more space in the current FPGAs for my filters than I was, but I still have lots of room to grow. I'm not half full on anything in the current.
So the RAM you're talking about, is that assigned in the FPGA?
Yeah, FPGAs, we always talk about them being a sea of gates. And each one of those little bitty pieces in there that might do an AND or whatever also has a flip-flop, so it has a little bit of RAM in it.
Mm-hmm.
It also has a shifter, so it's got 16 bits of RAM that it can run around like that. But over time, they discovered, well, people really like honest to goodness RAM, so they put SRAMs in the FPGAs. And the beauty of the RAM blocks in an FPGA are they can run as fast as the FPGA. If your FPGA can do things at 500 megahertz, your RAM can give you data at 500 megahertz.
Wow, that's impressive.
So having a lot of RAM that can run as fast as your multipliers is great because you're never waiting for data. You don't need a cache because the data's there.
Right.
It's so much faster than, because you can talk to any part of the RAM as fast as any other part of the RAM, it'll be there. The other thing they do is it's a dual port RAM. One side could be reading while another one's writing, or you could have two parts reading independently. So in the filters I'm using, I'm reading from the beginning of the coefficients for the first part of the data, and I'm reading from the backward side of the coefficients for the other side of the data. So I'm actually pushing both ways in the RAM as I go through, taking advantage of the dual ported. You can't do that in a regular computer efficiently.
Sure,
So
sure.
there's a lot of little things like that. Nice. While we're talking about the FPGA, one of the differences between the Mark II and the Mark I is the FPGAs in the Mark I had built-in multipliers that you could use as units to build up bigger multipliers. And they were 17-bit by 17-bit multipliers,
Okay.
giving you a 34-bit answer.
Yeah.
Actually, it was 18-bit signed against 18-bit signed, giving you a 36-bit answer. But if you're using unsigned, you can't get 18 bits. You can only get 17 bits.
Okay.
And so if you're trying to multiply two 18-bit numbers, 36-bit numbers together, well, it doesn't quite work. You can multiply 35-bit numbers together and you're okay by using two multipliers. Now, the FPGAs in the Mark II, instead of being 18 bits, they're 24 bits, not 25. So that means that if I want to do a 50 by 24-bit multiply, it only takes two multipliers in the Mark II, and it takes at least three, if not four, in the Mark I. So I got to save a lot of multipliers rewriting all of the filters. And so, that was pleasant. It made my life a lot easier.
Sure.
The filters were simpler.
Sure.
I didn't have to debug around the edges as much.
So if I were to sum up the differences that you've been describing, we've got galvanic isolation, which is lowering noise, jitter, and really having a dramatic effect. And that is also user selectable, if you will. We've got power factor correction. We've got power supplies that are completely isolated, and the potential for future upgrades that could be significant, possibly far more significant than what we enjoyed in the MK1 are there. Would that kind of sum it up? Or
yeah, I hesitate to promise things that I can't predict that I'm going to do. On the other hand, in the Mark I always sort of had a vague idea what I was going to do next.
Okay.
And perhaps some ideas are half baked for the one after that. And I never knew how I was going to get beyond those at all. But every time I do a release, I march one step ahead.
Sure.
I have no reason to believe that's not going to change on the Mark II, but I think I'm headed more for like a release a year, not a release every 3 months on the Mark II.
Okay. All right.
I already have two different sets of things that I want to do to improve the Mark II. One of them is enabled by things we found out really late in the Mark II production hardware. And by not having to work around that hardware, I can tune things a lot better and lowers the THD somewhat.
Mm-hmm.
So that's always welcome. It's not quite as useful as lowering noise across the board, but it's useful. And I've recently added another filter in the right place that so far people are saying is made the background blacker.
Mm-hmm.
That's always welcome.
Oh yeah, absolutely.
So those are two things that are definitely coming in the next releases. Now, I don't mean next month, although you might get a surprise, but it will be done before the end of the year. Before a year.
Yeah, great. So, me and the others listening to you, Ted, and by the way, thank you so much for taking your time on a Sunday. But again, what's the biggest difference? Is it the possibility of having, as you were saying, the huge changes that could in the future work wonders with this new FPGA? Or what's what's the single biggest thing that is going on here that makes this so much better? It's like the MK1 was and has been for years the best DAC that I've listened to. But when the MK2 came in, it was so much more alive, so much more. The sound stage goes on forever. I mean, I've never heard anything. We just had a customer write to me and said, in 40 years of doing high-end audio, I have never heard an improvement as big as the difference between MK1 and MK2. So what would you think is it the lowering of the noise? Is it the lowering of jitter? What is, how did you do
Um,
that?
well, jitter is a form of noise, but yeah, let me answer that two different ways.
Okay.
The simple answer is everything I touched, I tried to lower the noise.
Okay.
That was my goal everywhere because I know lowering noise makes things sound better. Because lower noise means a blacker background. That means the sound is just there rather than floating around in your room or whatever. A lower noise means you can hear little micro details, like
Mhm.
you can hear more when somebody's playing the violin, you can hear the bow that much better. That adds reality. You can hear vibrato in performers' voices that much better. That adds some reality. You can hear them breathing that much better because, when you peel away a little bit on the bottom of the noise, it helps everything.
Mhm.
It is the case that lowering jitter makes the bass better as well as the highs better across the board. And a lot of people on the Mark I could hear when I lowered jitter from release to release
Oh
and
yeah.
lowered noise. Um, One thing we didn't mention that we should have mentioned is we're also using better analog output transformers than on the Mark I.
Yes.
And these can handle higher things with less distortion, and they reach further into the bass and the treble than the
Mhm.
Mark I. And both of those are welcome.
And
So,
and I will tell you, they are a lot more expensive too.
yes, and we're by no means paying as much as we could for them, but because then nobody could afford the DAC at all.
Yeah, exactly.
Um, but these are good transformers, and the difference that upgrading them makes is non-trivial. Um, it adds to the realism as well, but still, everything comes from lower noise to a first approximation. Your lower noise means everything that's in your sound field is more precisely positioned. It's not noisy. They're not moving around relative to each other. It means that the bass and the treble of any given instrument are stable relative to each other. They're not moving around as much anymore. So, in some sense, when you look in your mind, when you see the sound stage, everything is in a much more better
Ah,
defined position,
yep.
and there's more room around it between that and the next thing. A violin trio now sounds like three violinists standing next to each other and playing,
Yep.
not a violin.
Yep.
Similarly, a double bass that's playing in unison with a bass. Now you hear a double bass playing in unison with the bass, not just some bass,
Yep. As you would have on the Mark One.
right? And one of my tests I do all the time is I've got everybody likes to cha cha cha. It's a recording from the early 50s, and I always thought it was recorded with too hot of a microphone. It just seemed a little shrill,
Yeah.
and the backup singers seemed to be all they were muddy, and I couldn't really tell in my head if where they were and what they were singing. Now it's not shrill. It's glorious.
Mm-hmm.
And you hear the individual backup singers in their positions. Now, everything back then was mixed left to right, center, right?
Yeah.
It wasn't the same kind of soundstage we're used to now. But the backup singers had incredibly well defined positions, which allowed me to hear it much better.
Mm-hmm.
So it's really important to have the image be as stable as possible in every direction. And so, I used more precise parts where I could
Sure.
to make the variance smaller. Because,
Mhm.
if the left channel is, 0.1% higher than the right channel, you're going to notice it.
You hear it.
It's
Yeah.
subtle.
Yep.
It's subtle. But, um, and we lowered the output impedance. That's just another random thing
That helps. That
that,
helps.
that
Better transformers,
for
lower
a lot
output
of
impedance.
systems, it makes a difference.
Yep. Well,
Um,
well, I'm sorry, go ahead.
and we actually, another thing that made a difference is we got rid of the attenuator that we used on the Mark One. The
Mhm.
Mark One had an ability to add a 20 dB analog attenuator for people's systems that it was just too hot for.
Right.
It let it let the Mark One work in more systems, but it had a sonic penalty. For
Absolutely.
some people, that penalty was very small, and indeed, some people like the sound better with the attenuator in. They
Not
were in the
me.
minority.
Not me.
Yes, they were in the minority, but they did exist. Um, and other people just played the Mark One with the volume down around 15, 20, which
Yeah.
for a lot of us, what?
Yeah.
that
No,
seems
no, no, no.
that
Keep it
seems
up
nuts.
at what was it? 85 was the best. And I notice now on the MK2, I'm running it at 100 constantly. And to me, and none of this, you got to dial it in at 82, and all that seems gone.
That's correct. With the Mark II, at one point, I figured out how I could get more low-level detail,
Yep.
but that algorithm failed with really loud music.
Hmm.
So I put a heuristic in there that when your music's quieter, nowhere near the top 6 dB, that it would use the quieter algorithm. But when the orchestra music really starts going, or Metallica or whatever, and you're using that top bit, I used the algorithm from previous releases.
Ah,
So it
okay.
switched between the old and the new at some point, and some people noticed that. And in essence, I'm using the algorithm that's quieter for the full range in the Mark II, because I got a chance to once again redesign the hardware and software so that they matched better, and I didn't have to
You
push
don't
it.
have to do all these
Well,
geriatrics.
and
Yeah.
one thing that one mistake that I made on the Mark One is that I told you that I could get by on 12 volts, and then I couldn't. Um,
I
so
remember.
so we had to artificially jack up the volume internally to get to where we are.
Hmm.
And that means that we're closer to the limits of what you can do in sigma delta modulators. So for the Mark II, we don't do that. So I'm using a quieter part of the sigma delta modulators than the Mark One.
Hmm.
So there'll be a little less compression on loud stuff.
Hmm.
Um, so louder music and transients impulses are going to sound cleaner on the Mark II because of that.
Hmm.
And that's actually a place that I'm going to make even better with the coming release.
Ted, I got to tell you, this DAC, I haven't talked to anybody that didn't instantly hear how great this DAC is. It is not just a little bit. I mean, look, we've had, from the MK1 and people listen to it and go, yeah, that sounds better. This is like, oh my God, this is huge. This is one of the single biggest changes I have ever heard in a piece of equipment. It is, it's, words fail me. You really have to hear how big of a difference this thing makes. It's unbelievable. Wow. It
Well,
it
here's
is.
something that you know but you haven't mentioned.
Okay.
When you go on the forum to look at people's feedback
Yeah.
with sound quality, one single person thought that he was a little disappointed that it wasn't a lot better than the Mark One, but everybody else is universal that
Oh
it's
my
just
gosh.
completely blows away the Mark One. You don't even want to put the Mark One back in your system after you have the unit.
No, and it
This is
takes
not
what, all
hyperbole.
of 5 minutes?
Yeah, this is not hyperbole. Everybody feels that way. And that one person I was mentioning hadn't broken it in yet.
Ah,
So I'm pretty sure he'll never go back after his first 100 hours or so. It's kind of interesting with the Mark One. I'm sure you remember. I don't know. I'm going to invent numbers here. Maybe a quarter of the people that got it heard something new and magical right out of the gate.
yep.
And then another set of people weren't really convinced until it broke in.
Mm-hmm.
And I don't know what different kinds of things they're listening for in these two things. But one thing I like about the Mark II is everybody, except that one guy, is hearing something magic right out of the gate.
Right
And
out of
then
the
it
gate.
only gets better.
Yes. Well, this has already gone on quite a while, and I don't want to have people falling off their chairs. Ted, it's quite an achievement. And any closing remarks on this Sunday afternoon for everybody?
I don't know. I guess I can just say personally, when I'm even playing the television through it,
I haven't
the
tried
center
that yet.
image is so rock solid that often I find myself looking up to see where something came from completely subconsciously. So even just it's enough more precise so that my phantom center is more rock solid than it used to be. So everything I do with this DAC sounds better and is pleasing to me, not just the audiophile things, right? How deep's the soundstage? How tall is the soundstage? I don't know what makes a tall soundstage. I just want it to be real.
Amen. That's well said, sir. Thank you, Ted. We really appreciate your time, and so valuable to learn all of this stuff. Thanks so much. And thanks for all the work that you've done for us. All right, everybody, take it easy. Bye.